So after going through all of this matrix elimination method to come up with solutions to roots, we haven't actually discussed the fact that we could actually use iteration as an alternative to the elimination technique. So for the system AX equals B, we can use each row to generate a set of iteration equations. So what I mean by that is our first x value, x1, is really just equal to b1 minus a12 multiplied by x2 all the way to a1n xn divided by our first coefficient a11. And in a similar fashion, xn is equal to bn minus an1 x1 all the way to an n minus 1 x of n minus 1 divided by our nth row and nth column element. So can you see that x1 first appears on the left side of our equations set, but by the end, well, at each row, it occurs in the second position. So if we estimate a value for x1, effectively we could estimate values for all elements in our set of equations. So for example, if we assumed that all x's, so let's just rip that out. So all x's are equal to 0, with x1 not being equal to 0, then x1 is quite simply equal to b1 over a11. We could then update the order of our remaining equations. So x2 would then become, with our first iteration, it's equal to b2 minus a21 x1 from our first iteration. Now remember, we assumed all the other x's to be 0, divided by a22. And we can carry this on until we converge upon a solution. And what do I mean by convergence? Well, we've seen this before. We want to make sure that the magnitude of our errors is really just the difference between our estimates from the previous, our current estimate and the estimates from the previous iteration, divided by xij. This is obviously multiplied by 100 to get a percent, and this is less than our tolerance. We call that epsilon s. So what would be a convergence criterion for this approach? Well, we can show that it's really just equal to AII, the magnitude of AII, being greater than the sum, and j equals 1 to n, j doesn't equal I, of the magnitude of aij. So that is that the diagonal element, aii, is always greater than the off-diagonal elements for each row.